Test time fine-tuning is a new paradigm to deep learning, right? It's something completely outside of the deep learning paradigm. What's the most efficient way to learn at test time? That's a very interesting question.
How did you encode the problems?
The whole point of ARC is they're gonna trick you. Whatever specialization you put in the input, you can create a problem that's adversarial to that tokenization scheme or special representation scheme for ARC problems, because it's so arbitrary. Problem is so different, right? It's a very new problem. But the really cool thing that you get out of this is you train this model to be a very weak, dumb contextualizer maybe, right? But that's what you're tuning for.
Transformers, even in a trivial sense, cannot do counting or copy. They just can't do it. You count up to 100 and you just say, can you count these numbers up? And it just fails abysmally.
What we do, which is really interesting, we prompt everything into the forward pass all at once. We're looking for people that are interested in changing the paradigm, going into test time compute, that like working in small and nimble teams, tackling really big problems.
Tufa Labs is a very, very exciting new research lab that's just started in Zurich. They are looking for amazing ML engineers to join their team. It's a very small team. If that sounds like you, go to tufalabs.ai. You might remember when we interviewed Mohamed last year. He's part of MindsAI, along with Jack Cole and Michael Hoddle, a couple of legends. Of course, they were acquired by Tufa Labs. They got the highest score on the ARC challenge, about 58%, and they've just released their paper where they spill the beans on how they did it. It's called Don't Throw the Baby Out with the Bathwater, How and Why Deep Learning for ARC. Now, the prevailing view has been that neural networks lack the necessary capabilities for abstract reasoning tasks, and at least to some extent, they proved that wrong. Consider this particular ARC puzzle. The task requires inferring complex transformational rules from minimal examples, a challenge where vanilla LLMs like GPT-4 get no better than around 10%. Now, Mohamed thinks that ARC puzzles are fundamentally perceptual reasoning problems. They incorporated the optimizer directly into the evaluation process, which allowed the overall approach to develop new abstractions during test time. And their methodology introduces two principal techniques. Number one, we've spoken about this a lot on the show, test time active fine-tuning, or what we've been referring to as test time active or transductive fine-tuning, where you generate synthetic training data derived from each puzzle's examples, and you fine-tune the model as you go. The second approach is what they call augment inference reverse vote, where you apply transformations to input puzzles, generate predictions, reverse the transformation, and implement a voting mechanism to identify a consistent solution. They found that the latter improved performance by 260%, with test time active fine-tuning providing an additional 300% improvement, which is how they yielded the highest score on ARC, about 58%. Now, another thing they found is that the model architecture scale has a greater impact than pre-training for building new abstractions. Larger models are simply more expressive, enabling better abstractions and reasoning during inference. Now, we are counting down the days until the version 2 of the ARC Prize. We are launching it on MLST on Monday, and I hope you're excited because we've got Francois coming over and he's going to tell us all about it. Suffice to say that all of the frontier models are going to be going down to negligible performance on it, and I'm excited to show you. See you on Monday and enjoy the show. Mo, you've been on the show before, but basically you won the ARC challenge with Jack and Michael. Technically you didn't win because you didn't choose to share your solution, but certainly in terms of the leaderboard, you guys did the best solution. Welcome back to MLST.
Thank you so much for having me. It's always a pleasure, Tim. It's really nice seeing you here in beautiful Vancouver. I feel like you're kind of a guest to me in Canada here. It's really nice seeing you. Thanks. Amazing. So congratulations on the incredible result. Tell me more. Thank you so much. We've been obsessed with the ARC challenge for a very long time. Me and Jack have been working on it for 2 years as part of the same team. Michael has been working on it. And we're now for 2 years, by the way. So we've always thought that this benchmark was gonna get more important, and this is the case now. At NeurIPS, lots more people know about the ARC challenge, and there's been lots of great popularization of it happening. I'm really happy to see that. yeah, we continued developing our methods based on kind of similar philosophies that we had, and I'm really excited to kind of dive deeper into those. And also, yeah, give you a little bit of some of our results that we're planning to share very soon in a paper.
Very cool. So by the time this goes out, you probably would have released that paper, so you can probably tell us some of the headline.
The paper is not going to be super interesting technically because we've shared our ideas before. We've shared them on MLST, and we're always like sharing. And if you look at like out of the top 10 current leaderboard on ARC, I don't know how many, but like maybe close to 80% were using similar ideas, very similar ideas in certain cases. So we were always like happy to share, and yeah, we've been pretty open about that, and we're happy to see everyone kind of converging on test time, fine tuning, and the voting mechanism that we found to be super useful.
Very cool. Well, why don't we break down like what are the key innovations, and maybe you can't talk about all of them, but what are some of the key innovations that led to your win?
Yeah, I'll preface this by saying like lots of the current methods are using very similar things, right? So it's like, and I'm very happy to see that everyone is kind of leveled up, and I'd be remiss to say it's not because of the amount of sharing we were doing. So I'm very happy to see that, and I'm happy to see what new innovations are going to come up now that we've all leveled up here. Let's break it down. So the innovation. So I think we should start with test time fine tuning because it's really the big one, and I like framing it in this way. Okay, so just to get the general idea. So there is a sense that, or you could say that test time fine-tuning is a new paradigm to deep learning, right? It's something that's completely outside of the deep learning paradigm, right? You're changing parameters at test time. That's not really, that's a fair thing to say, right? But there is a way to look at it in which it exactly fits the deep learning paradigm, and that was how we arrived at it. So the idea is we really see ARC as this perceptual problem, right? You have an interpretation problem. It's kind of subjective in a way because you have these biases, right? You're looking at the problem and you have an almost infinite set of possible transformations from inputs to outputs, right? And it's really hard to narrow down what you should look at, right? And it's really hard. Like imagine a riddle that there is a box, and inside it there is another object, and there are different types of objects, and it's really hard to find the right level of representation to start to even search around the solutions, right? So you kind of have to take it in all at once and hope that something pops up. It's very similar to looking at an image. There is an almost infinite set of different colors and different lightings, and they're all the same thing, but you have to contend with this infinity before you can kind of proceed to abstract over the image itself to say like, okay, now there are 4 apples, or you start counting, or first you have to identify the apple in infinite lighting, infinite coloring, right? And that perception part is really important in images, but we think it's really important in ARC also. So you could easily imagine, once you have the right level of abstraction, search becomes much easier, right? Searching for the right function is very, very easy. If I know this is the relevant object, I need to count, or I need to do something around this specific object, or this object-to-object mapping, right? So very, very important to get the right level of perception. So, okay, so what's the best way that we know of to tackle a novel perceptual problem? It's the deep learning paradigm, right? If you have, if you want to learn a new skill, right? A perceptual skill, you want to classify mugs. You start with an untrained network and you train it on a bunch of images of these mugs, right? And so we take that idea, but apply it on ARC. So the claim with ARC is completely novel at test time examples. So the logical thing to do, and you have to really take seriously this idea that ARC is the most important or one of the very difficult parts of it, not the most difficult, is this perception problem. So then you just apply that paradigm, but in test time, right? And you know, it's known to acquire skills really well. So you apply the whole paradigm to acquire skills at test time.
Right. So that's certainly true. So that there are things that neural networks can do that we cannot write programs to do. Right, just because they are, Chollet kind of distinguishes between perceptual problems and like type 2 problems or whatever. So many of those problems are perceptual problems. One really interesting thing though is that you guys, counter to people like Kevin Ellis, you are fans of solution space prediction. So you don't create intermediate Python functions. Is that the case?
Yeah, that's true. Yeah.
So that's a pretty huge kind of like strategy right there. So I have this intuition, and Chollet does, that there's something special about Python programs, right? And the special thing is mostly that they have this kind of compositionality, which means they can be composed together, they can be like decomposed into small parts, you can construct a library and you can like take bits together and so on. And we intuitively feel that neural networks, for whatever reason, they don't have this compositionality. Maybe we can make neural networks that do in the future, but right now they don't.
Yeah.
So people who are really bullish about neural networks, and certainly I think you guys are and Tufa is as well, think that no, actually they can do this kind of compositionality. They just need to be coaxed in the right way.
Yeah, that's a very poignant point, that it's absolutely true that neural networks by default are not compositional, and you need to do a lot of work to get them to be compositional, and that's you know, not easy to do, and we did do that work, and it took us a lot of time and to really understand that point, right? That you know, by default they're gonna just learn statistics, and it's not elegant because they're not composable. But I think and I'll speak to this later, that you know, you can, for a certain domain, you can get the biases deep enough, and the biases are really important, such that you're able to tune the reasoning part really easy. And in that case, in that sense, you do get compositionality, but it's not an elegant solution that you know, without the test time aspect, without putting the biases deep enough, you don't get that. So now what do you do, and how do you do that more efficiently? These are all things that we want to explore in the future. And we're going to do that at Tufa Labs. With the Python programs, there's something, again, that's really important. You can perceive the problem. If you perceive it right, you can take action in Python or in the neural space. I think that's fine, as long as you see the right level of abstraction. You have that dynamism inside the model to be able to do some correlations from input to output, and then match those correlations and force them in the other input to output, and then you know, make sure it generalizes, and then you can, after that, you can either output in Python or in a direct output manner, right?
Well, let me press on this a little bit, because I think this is potentially, you know, the most exciting part. So we have an intuition that Python programs are compositional, and I interviewed Laura Ruiz the other day. She's working at Cohere, and she did this paper showing that basically you train inference functions on neural networks, and then you get them to do fact retrieval, or you get them to do reasoning tasks, and you can see how much of the, you know, like how many of the source documents light up essentially based on the task. So when doing reasoning tasks, it had a very diffused activation in terms of the source documents. And what she noticed is that it was looking at code. So when calculating the slopes of lines and so on, it was looking at things on Stack Overflow, and it was looking at procedures of like how to perform some reasoning, and it was applying that in a very diffused way to a specific problem. So, yeah. So the fascinating thing is that even though it's not explicitly generating code, you can fine tune it on code, and code has some form of compositionality, yeah. And you can coax the neural network to do an approximate form of compositionality, even though you're doing solution space prediction. That is fascinating.
Yeah, one of the things that we do for pre-training. So code, I think there's another thing that's really another way of saying what you're saying about code. And by the way, I know about that work. It's really amazing work.
Yeah.
So with code, it's really hard to predict the next token. You have to contextualize a lot more. Like you have to know, okay, what are we doing? What is the exact name of the variable? What is the exact relevant variable here? With language, that's not the case. With language, you can shortcut, you can cheat easily, right? You can use like an inaccurate word and that'll probably be fine. You know, with code, you have to be very precise. And so you have to be very contextual, right? And I think that's like another way of kind of looking at the influence of code. And code pre-training has been shown to improve reasoning across many domains and in a few new papers now. So this thing has been reinforced. But yeah, training on code is really interesting. I also want to kind of go to this idea of tuning the reasoning. So you know, you mentioned that the neural networks, while they're solving this reasoning task, they're looking at code, right? I think framing the problem also matters in a very important way here. So first of all, we established that test time training gives you the generalization ability. Okay, so what do you have to do to what's the most efficient way to learn at test time? That's a very interesting question, right? And so what we do is we prompt everything in context, right? We're just speaking about contextualization ability, and that's a really important thing for us to maximize for ARC, right? Because if you're prompting things into ARC, like in the ARC format, you need the model to be as dynamic as possible, right, Tim? So you have your inputs and outputs, and now I have this test input, and the problem is so different, right? It's a very new problem. So contextualization and the ability of the model to kind of be steered is very, very important. And what we do, which is really interesting, we prompt everything into the forward pass all at once. So inputs and outputs, input and then test input, like new input, is all in the forward pass all at once. So it's one way to look at it, it's a measure of the novel contextualization ability of the transformer, right? But the really cool thing that you get out of this is you train this model to be a very weak, dumb contextualizer maybe, right? It doesn't, the modeling ability in the forward pass is not that good, but that's what you're tuning for. It's kind of like a meta model in a sense, right? That's what you're pre-training for, okay? And so the model is gonna be it's gonna learn reasoning patterns. It's not gonna learn exact transformations like Clem's work, right? So Clem's work is the function learns just the transformation, right? But our model, by putting everything in the forward pass in pre-training and you're training it over many different ARC riddles, right? So you're kind of saying, okay, the thing to learn here is this meta task of looking at the context and then generalizing from it, or doing your best at modeling from it. And so you have this weak meta model, and now that's much easier to tune than a Clem type model where you just have, for Clem's model, the encoder only receives one pair of input to output. You get stronger induction or regularization, I don't know what we want to call that, but with that model, but it's like, there are many possible, like you don't get that meta ability, right? There are many possible sets of transformations given only one instance, right? You need 2 or 3 instances to kind of narrow that infinity down. So you're training this meta model, and now tuning that meta model is a much easier task, right? Like that's really interesting. You kind of, like, again, the thing is you have a predictive model that's gonna be kind of wrong. You can just tune tiny pieces of it to get the reasoning to click, right? So that's really, really key. And it's work that is not super present in the literature. I didn't survey it super well, but there was one interesting paper, the MLC paper by Brandon Lake in Nature, which was looking at reasoning. They don't do test time training or anything like that, but implicitly there's a way to look at it where it's exactly this, actually. It's exactly doing what we're doing. So for that paper, what they do is they have this input to output kind of task that they want to learn. What they do is they retrieve similar things, they put them in context, and then they put the new thing, and then they do, that's their forward pass. Okay, and then they train over that, and that helps them do much better. So they're kind of training over that. So that's kind of test time tuning if you take that whole paradigm and put it at test time. So we train over that, but at test time, and it's the framing of the model as a meta model, and now the tunings that you have to do are much smaller. So I think that's maybe one of the biggest differences between our work and Clem's.
Can you just summarize that again, just so the audience understand it? So you said that you're doing more kind of training of the model before you do anything at test time. Can you explain that?
Yeah, so we do pre-train the models on ARC.
So you start with a language model, you know, like, I don't know what you use, maybe Llama or something like that.
T5 variant, long T5.
So you start with a T5 language model.
Yeah.
And what kind of a language model? It's not a normal, like, autoregressive language model.
It's an encoder-decoder. So that's, so it's an encoder-decoder, but it's, and it's pre-trained. So we don't train it from scratch. Pre-trained on language, which we think has that contextualization aspect a little more, right? And we also train it on code further. So then it also gets stronger emphasis on this contextualization ability, right? You want to train the best kind of forward pass steerable model, basically dynamic model that can change a lot based on its inputs. Not and that is possible with transformers, but only to a certain extent. So that's what we start with.
Even that is very interesting though, because no one else has done that. So you're starting with an antique model from about 2020, which is an encoder-decoder, which is something that doesn't really exist anymore. I mean, those were originally used for like machine translation tasks about 1 million years ago.
Yeah.
So and it's presumably trained on a tiny corpus compared to modern thing. I mean, it might be trained on like I don't know, like less than 1 billion tokens probably.
Yeah.
So you start with that, but the benefit of it is, I'm guessing it's a tiny model. It's like what, in the millions of parameters, like 340 million parameters or something.
Exactly. Yeah.
So it's a tiny model.
Yeah.
Start with that, then what?
So then we have this pre-training recipe that involves code. It involves auto-generated ARC tasks in various ways, and Jack did lots of really good work there, Jack Cole. So there's this magic recipe, but the bottom line is it has lots of code. It has lots of kind of synthetic tasks. By the way, the amount, like the total number of new tasks is not big, right? It's not like we are able to sit down and generate so many synthetic riddle generators, right? Like the total number of new concepts in pre-training is low, but there's an important thing that we think is happening during pre-training, even with the few number of number of concepts trained. But we have a recipe that has some code, and it has some synthetic tasks, and then we get our pre-trained ARC model, right?
Okay.
Now we go into the test time where we feed everything into in the forward pass like we were doing in pre-training, and then so all of the instances are in the forward pass, and then we get the test input, the new input that we need to predict the output for. That's also in the forward pass, and we need to predict the output. And what I was saying about tuning the reasoning is the framing of the problem is really important, right? Everything in the input, you need to kind of learn, okay, how do I compare the input and then kind of get at a very almost okay function, but probably not okay in very important ways. That's already very, very close to your solution. So now you can test time tune and kind of search over the reasoning, tune the reasoning, rather than a different way of looking at it, right? And then, so first of all, that compares to like the MLC work. It compares to lots of ideas where you're kind of, when you frame the problem in a meta way, you give the model more to learn. It kind of is always the best thing to do in the forward pass, and then you have to kind of scaffold and tune and do everything else. But you're kind of halfway there, with that step. And so the tuning is much less work at that point.
Okay. At test time, so you call it the forward pass. So you put the test instances in there, you represent it in a really clever way that kind of helps the language model, the seek-to-seek model do its thing, and then you do some green blatting, for want of a better term. You do lots of sampling until you get ones that fit all of the specifications. Do you do any augmentation in the forward pass?
Yeah, so the forward pass is just like prompting the model with the representation of the board, and the representation isn't super special. It's just a plain representation. So just a plain representation into the model. We don't do any filtering, if that's what you mean by green blatting. It's a very transductive, like you just produce the output directly. So we can't do any filtering actually.
Right, but do you do loads and loads of sampling until you get ones that you think are good?
Yeah, so we have a method of voting that we also introduce in the paper. And voting, I think, is especially suited to ARC. So, and it follows this idea of there are many ways that you can be wrong about an ARC riddle, but there's only one correct solution. So, just try all of these ways and then hope that, the majority vote is going to go to the only right way to do it right. So yeah, we do that.
And tell me more about the voting.
I think that summarizes it pretty well. We do augmentation. So there are many ways to sample things out of a model. One way to sample something out of a model is beam search, right? Or you could do temperature-based sampling, which I don't think is a good idea for ARC, because again, like if you just get bad RNG, you're kind of done for. But beam search is really interesting because ARC is very special because it's only one right way to do it right. So you can imagine all of these beams, and the model is kind of uncertain about a certain next token, right? And that's totally fair. So we're gonna take a beam, we're gonna try all of them, and then iteratively, if you made the wrong decision, you're gonna be kind of lost, right? Like in the pixel space, if you're outputting, if you've made the wrong decision, you're going to be very lost because you don't know, like a mistake is already done. Obviously, these models can't backtrack. So, okay, how do you really continue after a mistake? It's unclear. Things are ambiguous, so that the probabilities are going to disperse, and then these are going to fall. These beams are going to fall. But if you've done the right thing, you're going to be more and more certain of the next token. So that's one aspect, that one way that we do, we get the samples, but we have like a kind of a variety of ways that we get samples for voting. We go into it a little bit more in the paper that will hopefully be out. Yeah, so that's the voting.
That was the sampling. How do you do the voting?
So it's just majority vote.
Oh, okay. And you said that there's only one way of getting it right, but aren't there uncountably many ways of getting it right?
Yeah, well, there's only one way with the human priors and with the ARC core knowledge of getting it right, hopefully. Otherwise, it's an ill-designed riddle, right? Like for an ARC riddle, there's only one correct answer officially, but of course you can have different systems that have different biases that they think this is the right way and so on. But hopefully it's very clear for the human biases and the core knowledge priors that there's only one way of getting right.
We should explore that. So the ridiculous example is I could have like a program which says, if you see this specification, then give this answer. If you see this specification, then you give this answer. And if you see the third one, then give this answer. So it's just like explicitly encoding the answers without any like generalization or whatever. And you're making the argument that because we have a certain structure of priors that can be composed in a certain way, you think that it's very unlikely that it will find a solution other than the ones which humans would agree on in that compositional space.
Well, that's what we hope to do with the training, right? So with the pre-training, that's what we hope to encode, right? We hope to encode two things: the priors really, really well. And by the way, I really want to get into prior encoding also, and what that means, because there's lots of theorizing about that we get, and there's lots of people like saying, okay, you're memorizing certain reasoning patterns and so on. So let's pin that for later, but that's what we're hoping to do with the pre-training. We're hoping to get the right priors and the right kind of core knowledge into the model in such a way where it only outputs the relevant right solution. But the second thing we want to do is we want to make the model steerable, right, for a new riddle, to not rely on the priors too much and to be able to actually produce the right one that generalizes. So it's kind of this very difficult balance. You want the model to be contextual, but also have the priors very deeply in there to be able to use them to search.
Yeah, so there's a trade-off between flexibility and correctness. The reason I asked this is on Wending and Kevin's paper, they said that on because they did an ensemble with induction and transduction, but they favored the induction. And I say transduction, they're both transduction, but they said they had a 9% false positive rate on the explicit function generation, which meant that it was creating functions which gave the correct answer, but was actually wrong.
Yeah.
So it worked on the test specification, but it was actually wrong.
Yeah. Yeah.
But have you seen that?
So we don't output programs, so we haven't seen that, but you can have transductive, in my definition of transductive, like you can have intra-riddle transductive Python programs, meaning just like you said earlier, like if this is the question, give me this answer. If this is the input board, give me this answer. You can have that with Python programs. You can have overfit Python programs, right? Which just means that they didn't get the right prior from this one and this one and this one to be able to generalize to new ones.
Exactly.
Yeah.
Exactly.
Yeah.
Yeah. So how much of an issue was that for you guys?
Well, we kind of just sidestep this whole thing, and we just kind of find different ways of giving feedback to the model, i.e. test time fine-tuning. So to kind of hope that the model, the built-in model kind of has the best chance to generalize to the new test riddle. And so basically the answer to that is everything we do at test time, right? We test time tune, which means, you start with the initial kind of guess from the model based on the ICL, the in-context learning, or whatever you want to call it, the contextualization ability of the model. And then you tune that. And what's happening is there's an implicit model inside, like there's an implicit kind of transformation function, you can say, inside the model that is getting tuned, right? That implicit model is giving a guess, and then the guess is incorrect in maybe major, maybe minor ways, and it's getting the feedback through gradient descent, and it's updating that implicit model through the weights, and then it's giving another guess, right? And another guess. So that's test time tuning. And then the hope is, that ARC has a perceptual problem, and that neural networks can learn these generalized perceptual problems if you put them in domain and if you tune the reasoning that way. So I guess that's how we deal with it.
How did you encode the problems?
It's a very plain, numbers as text. So there's nothing special there.
Okay.
Absolutely nothing special. This is a very interesting question. You shouldn't, in my opinion, you shouldn't generate any special representation for ARC. The whole point of ARC is they're going to trick you. Whatever specialization you put in the input, you can create a problem that's adversarial to that tokenization scheme or special representation scheme for ARC problems, because it's so arbitrary, right? The main point of ARC is raw. You get the problem raw, and then be flexible about combining it, because it's going to be novel and it's going to be raw. So don't this is another thing, VLMs are really bad for ARC, right? Maybe this is giving a lot of alpha to people, but because I think for some people, for a big majority of people, the first thing they try is oh yeah, we need this is a visual problem, let's use a VLM, right? But that's a really bad idea. And that gets to some of the stuff I was seeing at NeurIPS, which is people are coming up with lots of data sets where VLMs do really bad. Like the 6-finger problem, right? If you have a hand with 6 fingers, you give it to a VLM, ask it how many fingers, it'll tell you 5, right? Why? Because the VLM is a fixed representation machine. This really gets to the core of ARC. If you want to understand ARC, you need to understand that you need raw representations into the transformer rather than pre-encoding some stuff. So the frozen encoder in most VLMs, it will take some kind of perspective pre-existing perspective on the ARC problem, but you haven't seen the rest of the input-output pairs yet. You don't know what the right framing is. You're doing that, you're guessing, and there are many ways that you could be wrong. It's the same thing with the 6-finger, right? With the VLM only knows a certain things, and it's gonna give you in the output tokens a representation of only that framing on certain things, like whether it's a hand or a leg. It's not flexible enough to be able to recombine. It doesn't know what the question is also. Like with a VLM, you already encoded the image before asking the question, I need to count the fingers in the image, so that the transformer model and the VLM encoder can't condition on that.
A couple of things on that. I mean, there's the notion of, Greenblatt did GPT-4o, the vision model, but I'm not entirely sure how that works. But the best way to do a visual model is to have it multimodal. So it's a language model and it's a vision model all in one, and it can do some kind of crossover between them. So there's the notion of whether having a vision model actually helps with ARC, or whether it's better to think of it as a reasoning problem, and whether to kind of like skip the interpretation part and give it a structured representation. That maybe we should start with that. I mean, do you think in principle whether we had a strong multimodal model which could transfer between the reasoning domain and the visual perception domain, it will work? Or the other point of your statement was that it's not flexible enough. But could we not do test time training and all of this transduction stuff with a VLM as well?
Yeah, you could. I just don't think it's elegant. I think it could get you to like 60% or whatever, but it's not gonna get you to 100% of the way there unless you change the architecture. So like I'm making a statement about a specific architecture, just to be clear. Like multimodality might help. The thing that I'm advocating for is you need a flat representation and an intermixing. So you could have vision patches intermixed with language tokens, and they all condition on each other. That seems reasonable. And but if you kind of have a pre-encoding that is frozen and you don't test time tune, that's just a bad idea. If you do test time tune, maybe that works, but again, it's this crutch. It's not reliable. It's better to just really focus on contextualization and on being flexible, because that's the point of ARC, right? And it's a very, very good benchmark because of that, because it found a way to test that. And I think one thing that's really good about our approach is there's a very different way of seeing it. Like, okay, if you want to measure the contextualization ability, the true contextualization ability of these models, of these architectures, then one thing you could do is just prompt it in the forward pass and see if it's able to solve it. So that's a really cool way of attempting to solve ARC. Obviously, that's what we're doing. So I think that, but that allows you to ask certain research questions that I'm really excited to answer at Tufa Labs. So it's not just about solving ARC. You could start framing things about measuring what transformers are doing, or the contextualization ability. I hope more people start doing that as well.
So one of the really cool things about test time compute, I don't know if you saw, Hugging Face have just released this kind of like O1 type thing, and they're showing that they can make a 1 billion parameter llama solve the same types of math problems as, like a vanilla 8 billion llama model. So what it seems to do is it gives you this ability to make a small model behave as if it's a big model. And that seems to be a superpower.
I'm not familiar with that release that Hugging Face did, so I can't comment on it. I can give you some more details about how our models scale on the hidden test set. So I think that's really interesting, something people really want to know. So so what do the scaling laws look like for the hidden test set that is just completely uncontaminated, right? By the way, the public
not completely.
The hidden test set?
Well, yeah, I think there is a potential objection that because we have now hit the hidden test set a lot of times, that there's some unintentional information leakage. Could you comment on that?
I think the information leakage, like from an information theory perspective, is very, very low. But I'll tell you what we are trying to do with the information leakage. We're trying to make it algorithmic, right? Like there's information leakage about the type of things that work on ARC, and that was the kind of the hope. but I don't see it as significant at all, honestly. The ARC data set was actually available for 100 submissions a day for like a couple of years, and people didn't seem to kind of like gain too much from that. We didn't gain too much from that. We weren't honestly using it that much. I think I'd say it's very minimal.
Yeah, because Chollet thinks that the reason he needs to make the next version of the ARC challenge is that if it's not overfit now, it kind of is, but just in a latent way. So he says that when you look at the ensemble of all of the various different approaches to ARC, even back in 2020, the ensemble was getting about 49%. So he said that, if you did a targeted, imagine we're like security researchers. That's what they do. They look for sources of entropy and they mix things together in a targeted way. And so he said, even though it hadn't really been attacked in this way yet, it's only a matter of time until it was.
Yeah. I mean, I think that's fine. I think it's good to refresh the data set and also maybe to remove the brute forceable one. So yeah, I mean, when I spoke to Francois a little bit, and he mentioned that even in his talk, he also mentioned the aspect of, okay, I'm gonna find out the brute forceable ones, right? Because that was the main approach in 2020, and I'm gonna remove those. I think that could be a good thing that you do. I do think the domain is so huge, and the possible variation in the ARC riddles is so big that it's totally fine to kind of use it. But maybe, yeah, like again, from an information theory perspective, the bits are not that much, but I mean, yeah, who knows? I'm totally fine with a new ARC data set that is harder. I think we're up for the challenge. The refreshment is good. The guys, I spoke to them a little bit, they're doing really good calibration with human testing to make sure that the data sets are well calibrated. So yeah, it's gonna be fun.
Chollet is quite bearish about some of the sort of the test time compute strategies that are being used, and maybe could you just reflect on why that is and what you think he would rather people did?
Yeah, he spoke about that a little in his talk. So he's bearish on test time compute, or the specific strategies that people are using for test time compute?
I think both. And I asked him, like, what would you do? Because he's doing his own startup now, and he has advocated almost for something that resembles the original DreamCoder. So he thinks that we should have. So first of all, he's a big program space guy. So he thinks that there are inherent limits in compositionality and whatnot using neural networks. So we should do the program space thing, whether it's a DSL or an actual programming language. I can't remember exactly what he said. Let's say programming language. And he says that we should have a neurally guided search, which is what the original DreamCoder thing did.
The reason I don't like DreamCoder type approaches is not because of DreamCoder specifically, and I spoke to like even Kevin Ellis about this, and they it's interesting their current approach, right? When you consider that he was the first author there. But so I think there are two kind of things that you have to focus on, especially when talking about DreamCoder. The output space, that's what Kevin Ellis mentioned. It's too restrictive, right? This lambda calculus, it's very inflexible, right? And that's something also that I think, like in my opinion, generating Python programs is hard. If I ask you to write the Python program for certain ARC riddles, could take you up to like 30 minutes, even if you're a good programmer, maybe 10 minutes to 30 minutes. But if I ask you to color them in, you can do that instantly. And that gets to like Piaget's theory of like incremental kind of development. So you can be in a game without being able to perfectly describe the rules of the game, but you can act in the game. So you can color the things, you can represent the thing and act in it, but the level of being able to fully specify the rules of the game and write them down, you don't have to have that. That's a higher level according to Piaget. So that exactly like hits it home to me. So that's the first problem with DreamCoder. The second problem is it just doesn't focus on the perception, right? It could, and if it did, maybe it would do well, but it doesn't. And I think the main thing should be, okay, how are you tackling being flexible in the perception space, and then you can go on to do whatever you like to learn programs in the sleep phase and compose them, and all of that stuff is fine. But the first question is that.
So that's exactly right. And what's also interesting is that Kevin has abandoned using DSLs. So he has, with open arms, embraced language models. And why is that? Well, it's because, as you were just saying, Python code is Turing complete. You can represent any concept. It's incredibly flexible. The reason why he didn't generate Python code in the first place was because there was this intractable search problem. It wouldn't have been possible. Now with language models, we can. And it's because language models encode our knowledge, our notions of what's interesting, even just basic priors that we couldn't even put into words, like the complexity of a program and the intuition and creativity and all of this kind of stuff. So now we can generate these programs and we can mix them and remix them and do all of this kind of stuff. Everyone at Neurops is doing the same thing. I guess the question to you is, this was a restricted compute benchmark, so of course you made certain trade-offs that you wouldn't make otherwise. Like now at Tufa Labs, you've got all of the compute in the world, all the time in the world. What would you do differently?
That's a great question. Okay, I think the most interesting thing to me right now is the thing I mentioned about prompting everything in the forward pass at once and measuring the transformer ability, innate ability, and then tuning the reasoning, these types of lines. So there's so many angles to tackle ARC. So it's not about it's the compute to do many experiments and to tackle the different angles and to get people on that will help and that are really interested in tackling these things and interested in thinking along these same lines, right? Like transformers are really bad at ARC. That's the statement that Chollet or like language models really bad at ARC, and they are. But let's measure it and let's try crazy ideas to get them to improve. That's what I'm after.
Tell me about this paper that you're writing with Jack and Michael.
Me and Jack are working on a paper to outline kind of the test time tuning. There's been papers now that outline the technical content of what we have, but we wanted to put the paper out there for people to cite the original kind of source. And people right now, by the way, are citing our MLST podcast.
No way.
Yeah, like lots of papers.
Really?
Yeah, the test time paper by MIT, by Ekin, cites the podcast. Like lots of people cite that MLST video podcast, which is not great, right?
Good for me. Yeah, it's probably because you didn't have it in writing anywhere.
Yeah.
Folks,
Exactly.
You can continue to cite the MLST podcast as much as you want.
I mean, that's actually amazing. You should have like a kind of a counter. I hope people do that more, but I also want to put a paper out there so that people can cite the written work and we can track it better. But yeah, I think this is a great format. We shared a lot about our method and people got inspired by it and implemented it and put a lot of papers out. So we want to put our paper there.
Yeah.
But technically it's very similar. Like with the stuff we're doing now, it's not far away from the stuff everyone else is doing. Some people are complaining about us not open sourcing, but again, the stuff is already out there, and it's, I'd be more worried about some prof told me this. I'm more worried about OpenAI not open sourcing rather than MindsAI. So I think that's the key thing, and another key thing is we're working on more papers, not just that one. That explore different angles, and we're going to be putting lots of stuff out there in the very near future, and I'm super excited about that.
Quick point on that. Why did you not open source the paper, the approach, and already put more out there? We
were in a very tough position from many different angles. So the guys, there was the requirement for open sourcing was a little too extensive. So they required weights, but also training a code or training examples and the entire test time code. So there was a lot of things. We felt like, with Michael's DSL that so many people are now using and have cited for everything ARC related, for test time tuning and voting that everyone is using to get the top scores. We've contributed a lot to the community, there was kind of a little too much, especially for us targeting that 85%, right? So it's just kind of the incentive structure really didn't make sense. If you look at the prize money and the potential gain. So it was kind of, I think lots of people were making the comment, the incentive structure, if you don't get 85% from the first competition, just wasn't great. So, we're super excited to do that moving forward. And also the competition team have told us that they're working on that absolutely, and they've taken that feedback.
Just to be clear to the audience, what was the incentive, given that you got, was it around 56, 57%?
Yeah.
What was the incentive? I mean, if you did open it up, what would you have got?
Yeah, that's a very good question. So by the way, just for reference, we started out at 33% at the beginning of the competition. So we did all of the work to get it to 55.5. We even got 58 score on the hidden set, but it wasn't on the leaderboard because the time had passed. Right. But so we moved up a lot, and what we would have gotten was 25,000 US dollars, right? Like after taxes, you know what I mean? Like not not a huge incentive. But again, like just want to say it was a great competition, and the guys did a lot to put the word of ARC out there and into the world, and they've taken that feedback, and we have also up-leveled the community and shared a lot. So I feel like we're both happy, and we don't need to like kind of dwell on it too much, and we can just look forward for next year.
You guys are now working with Tufa AI Labs in Zurich. As I understand, Tufa have acquired MindsAI.
Yeah.
Is that, yeah, tell me the story.
Yeah, we are now, so the whole team is now working out of Tufa Labs. We have a lot of funding. We have a lot of compute coming in. So we're going to be purely focused on ARC for the first around year, and different angles to ARC. Again, we're working on not just this paper, but another one and a couple of other angles also that we hope turn into paper. So we are going to be putting stuff out there, and we're hiring, and we have compute coming. So do apply if all of that, if any of that sounds interesting to you. We are going to, we have also plans for things to do after ARC. Like, again, we spoke a little bit about this with the compositionality, right, of these large language models. It's not there. How can we get them there in a more general format? Lots of system 2 goals. And test time obviously is a very ripe area, and more generally for research. So we're going to be exploring all of that beyond ARC.
Yeah, all of that is very, very exciting. So yeah, the compositionality problem, Clem was saying the same thing. I mean, that is the golden ticket. If we can solve the compositionality problem, I think reasoning opens up. But presumably, though, the approaches that you're going to be working on now are going to be slightly broader than what was appropriate for this particular benchmark. So you're going to be doing a few things differently. What particular kind of strategies and approaches are you going to be looking at now?
Different creative ways of doing test time is really interesting. That I'm also interested in. But first I'll say you always have to target the 100% with ARC. You can't. It's very hard to optimize, for a certain competition for something like ARC, or it's a really bad idea. It's not gonna give you lots of score because of the how private the data set is, and you can't make guesses about it. It's just formulated in a really nice way where you have to kind of go for broke, whether you are working in a small team with very little funding or with a lot more funding. I think it kind of is the same, but what we get now is different angles, right? And research angle and the competition angle, and these are super well aligned, by the way. Like, they mesh together really well. So just more angles of that. I'm also just thinking about different benchmarks around ARC. I have I think some really good ideas there. The ARC is a special format, I think, that allows you to benchmark certain things. Maybe we can go into that at another time.
What do you think will happen when Chollet releases the new version of ARC? And by the way, one thing that Kevin and Zena said, which I didn't predict, was that has ARC become a lame duck benchmark now that Chollet has said he's going to invalidate it next year?
Invalidated meaning?
He's making a new version of it. So it's almost like, are you wasting your time working on ARC 1 when everything changes with Arc 2?
So I think Arc 2 is going to be the same format as Arc 1, right? So I think what's going to happen is it's just going to get harder.
So what he said to me was that he's employing loads and loads of humans to design and select tasks that are at the appropriate level of difficulty.
Yeah.
So some tasks are insanely difficult and most humans don't get them right, and some are like too easy. And even then there's an interesting overlap between what's easy for a human and what's easy for a computer.
Yeah.
Chollet, of course, is a big believer that they are a proxy for intelligence, that there should be some kind of G factor or generalization between them. The other thing I wasn't entirely clear on is he protecting Arc 2, the second version of Arc, through diversity? So just reducing information leakage through sheer diversity, or is he talking about creating a dynamic benchmark which is almost entirely impervious to overfitting?
I will say this. So I was talking to Chollet and I asked him, are you going to have a dynamic benchmark where you iteratively, or you have some kind of iterative framework where you can ask for more? And he did say, no, it's going to be the same format, just different data and possibly very likely more difficult in whatever way they are calibrating for. So I think one thing that Chollet speaks about related to your first question is the getting the right level and so on. This idea of idiosyncratic riddles, right? Meaning like one-off riddles, right? Those riddles that are so creative. I think it requires real creativity to come up with those riddles, right? Like they're so creative, they're just kind of very novel, right? Like you can't label them. If you were working on a labeling approach for Arc and you're trying to find the right label, it would be hard to categorize, right? They're one-offs. And I think what he's going to do is have a lot more of these idiosyncratic riddles. And I think that's interesting. I think that's a good thing. But I also think that the original Arc formulation was already good enough, and it's already enough for us to come up with new methods. And even if it remained the same, I think there's still lots of angles where you can measure, generalization transformers, improve on it, even with this fixed thing. And I do think it gets solved with scale. Like I think Arc V1, give us 4 3090s or 2 3090s and more time on the problem next year, and absolutely we get to 85%. For Arc V1. So I do think it scales, and I do have some data on that with the hidden test set that it does scale actually in a very interesting way that you wouldn't expect. But yeah, no, I think it does scale, and I'm okay with more idiosyncratic riddles. I think maybe that would tune our signal for what is generalization a little bit better. So they're putting a lot of hard work into that, and I'm excited for it. Maybe if they do listen to this, just one request or hope that they also open up the V1 again, so that we can have a kind of just a benchmark for progress on the methods, right? Like we know the scores really well on V1. If we can still submit to V1, even though now there's a V2 and it's very different, if we can still submit to V1, that'd be really good to have maybe as like a validation set or a kind of another benchmark, you know what I mean?
Yeah. I mean, Chollet's measure of intelligence was so fascinating because he was talking about this adaptation, this and being able to create a new skill program in the response of novelty. And if you think about it, it's not a foregone conclusion. This is actually a very difficult thing to do from a psychological point of view, because you're trying to create a general benchmark that, given the kind of the base knowledge of the average person, that they would be able to do this generalization. You gave the example of the one-offs. That would be why our manhole covers round. These ridiculous riddles that they used to use at Microsoft to hire people, and only 1 in 1,000 people. So the information gain on that is basically zero. So you need to create a set of programs that the average people with their basis priors would be able to do. And Arc solved that really well. And I think maybe Chollet doesn't get enough credit that he did so cleverly select challenges that would work well for. Yeah. And of course, now he needs to diversify across that. One other quick question is, in your experimentation, did you notice patterns? Which types of tasks are you failing on and which ones are you doing well on?
That's a good question. So Prof. Melanie Mitchell has a great benchmark.
ConceptARC, yeah,
Yeah,
yeah.
yeah. Yeah, she's been thinking about this for a long time, and she has lots of great ideas there. And one thing I'm noting is I've spoken to lots of people that are in the benchmark and are using neural methods, and they all say, yeah, concept arc counting is the lowest, right?
Yeah.
What, like, it's just a thing. And if you try to add more counting based riddles, or I don't think you should add priors. We haven't tried that, like in priors in terms of like feature engineering, and that kind of a thing is not good. But yeah, just counting for some reason is really abysmal for neural networks.
Yeah. And I can tell you why. So I interviewed two guys at DeepMind on Monday, and they've studied this in self-attention transformers. They actually say it's because of representational squashing. I won't spoil the surprise. You can watch the interview, but there's a couple of problems with transformers that, because of the way they're set up, they almost all of the attention gets kind of like focused on in the limit. Actually, if you scale transformers all the way up, all of the attention gets focused on the first token. And there's also another problem with the Softmax function that like creates this kind of like directedness.
Yeah.
And for certain types of reasoning tasks, you want it to be directed.
Yeah.
And for certain types of creative reasoning, you want it to be diffuse. But they were basically saying that transformers, like even in a trivial sense, cannot do counting or copy. They just can't do it. Like you can give it a trivial example where you say, you count up to 100 and you just say, like, can you count these numbers up? And it just fails abysmally straight away. Copying is an interesting example, because even if you use tools, like people say, well, it's okay, you can just use tools. You can just like, stick it into a Python tool. If you can't even copy the tokens into the tool, then you can't do that. But the upside of this is all we need to do is fix this problem. Right? All we need to do is whatever the problem is in these architectures, if we can make them copy and count, then maybe all of these problems will just disappear.
Yeah, it's exactly that. You need to kind of dive really deep into the architecture and see where the problem is. And in this case, yeah, it can be very clear what the problem is, right? The softmax is a max, kind of a cheat code way to kind of achieve something similar to a max. And you can see how that would bottleneck things. You can also see how more layers, there's some really brilliant postdoc told me this. He told me, you want to do the processing in a single layer. You don't want to do the processing of these things like in one layer. You want to do them as you go up the layers. And what he means is, if you add, or if you're counting all in one layer, that means you're overfitting, right? Why? Because you're not really running an algorithm, right? You're just kind of taking this feature, and you're doing it in this one layer. But if you just have one layer, right, that goes and attends to this thing and updates itself, and then goes and updates this thing, that's the general algorithm, right, that you want. It's not this like heuristic kind of MLP in one single layer that will just kind of I get this feature and this feature and this feature and do everything in one layer. That's not what you want. And so lots of ways of doing that that I, again, super excited to explore. And I think, you hit the nail on the head there with what you just described.
Mo, it's been amazing to have you here. Thanks so much for coming on.
Thank you so much.